Hello, and welcome back. Today, I am very excited to begin implementing the overlap tests in code. The plan is to go over non-mesh contacts in this video, and then in the next one, I will be going over the mesh collisions. We'll start today with the sphere versus sphere test, and then continue on to capsules and then hulls. However, you'll quickly start to see a trend, and that it's just spheres all the way down. Our primary objective is to find a pair of closest points on the two bodies, and then generate a contact normal from body 0 to body 1. We'll also be calculating the overlap or interpenetration of the two bodies. The contact normal as well as the penetration values will be used later in the contact resolver to correct the collision. There's a lot to cover, so let's jump right into it. Starting with spheres, we define our overlap condition as the distance between the center of the spheres being less than their combined radii. First, calculate the center span of the two spheres and then add the radii and evaluate the overlap condition. If the condition fails, we return false with no collision. Or, if the condition returns true, we continue on and create the contact manifold data. Calculating the contact normal is simple. You just normalize the center span, and then computing the contact point isn't much harder. You find the surface points on each sphere using the normal, and then once you have the surface points, the contact point is found by taking the average of the surface points. Next, the interpenetration is the distance between the spheres minus the combined radii. Finally, store the contact information in the contact manifold and return true. And also, to calculate the surface point for sphere 1, you would actually want to go against the normal, not with it. So surface point 1 should be the center minus the normal times the radius. Moving on to sphere versus capsule, we basically use the same overlap definition, except this time we're going to be creating a virtual sphere around L, which is the closest point on the line segment C from the sphere. So to start off by computing the point L, once we have that, it's basically just the sphere-sphere problem again. Then we evaluate the overlap function and compute the distance and normal, then the contact points. And once we have the contact points, we average them together to create the collision point. And surface points. Once we have the surface points, we average them together to create the collision point. And the interpenetration is the distance minus the combined radii. Add the information into the contact manifold, and then return true. Moving on to the last sphere test for today, we define the overlap of a sphere in a hull in a similar manner to a sphere in a capsule. Starting off, we still want to compute the closest point on the hull like we did with the capsule. And to do that, we'll use the GJK algorithm. I know I've said this before, but for now, GJK and SAT, as well as their surrounding structures, are going to be black boxes for now. However, after these overlap test videos are finished, I will be going right into those. If GJK succeeds, we once again evaluate the overlap function, and here they should actually be checking the radius squared and not just the radius. Nonetheless, if we detect our overlap condition, before we generate the contact information, we must compute the closest point on the hull in walled space. The closest point returned by GJK is in a different space called CSO, or the configuration space obstacle. I'll explain this in more detail when going over GJK, but for now, we'll loop over each point of the simplex generated by GJK, and then compute the contribution of the support vertex from the hull and add it into the hull contact point. Once that loop finishes, we repeat the contact generation process as normal. The first GJK approach will only work when the center of the sphere is outside of the hull. If GJK fails, we next assume a deep contact and test for a separating axis with the sphere and the hull. Should a separating axis not be found, we use the information returned by SAT to compute the contact information. Next, we'll move on to the capsule test. Starting with capsule versus capsule, we define again an overlap test similar to sphere versus sphere. We'll begin the test by computing the closest points on each capsule segment from the other segment. And one note I would like to mention is almost all of the closest point functions and the like, except for the clipping that comes later, those functions come from Christer Eriksson's real-time collision detection book, which I'll make sure to leave a link to below, as well as the rest of the reference material. After we have the closest points, we evaluate our overlap function and continue on if the condition succeeds. We next test if the capsules can be in a stacked configuration. I was on the fence about showing this part of the code as I've been having issues with capsule stacking here as well as with hulls, but this morning I was actually able to reason that the problem is likely inside of the contact resolver, as a lot of the variability witnessed is tied to that system, but that's beyond the scope for now. So testing for the stack configuration is simple. First, find the capsule segment normals and test if they're practically collinear. If the stack condition passes, we swap the capsule segment points if needed, and then clip the capsule segment against the side planes of each other capsule. Once we have the clipped points, we compute the closest point on segment 1 from segment 0 and calculate the contact normal. From there, create two virtual spheres and do the sphere versus sphere calculations. If the stack condition fails, simply use the closest points returned from the beginning of the test and do the sphere versus sphere calculations from there. Simply return true, and we're done with capsules. The last capsule test for today will be capsule versus hull, and in a similar fashion, we will lift the overlap definition from sphere versus hull. We also basically repeat the same steps. First, assume a shallow contact and run GJK. If GJK succeeds, evaluate the overlap condition. Assuming overlap is detected, we'll compute the hull contact point, but not the segment point. I found that the closest point reconstructed from the simplex isn't the best candidate to use, since the hull contact point ends up becoming the sole contributor to the contact calculation. Instead, once the hull contact point is computed, I then use that as the query point in the closest point from line segment calculation to return the closest point on the line segment. After the segment point is computed, the contact normal and distances are calculated the same as before. However, unlike sphere versus hull, but like capsule versus capsule, We would like to be able to generate multiple contact points to support the capsule segment when resting on a whole face. First, check if the contact normal is anti-parallel to the face normal and perpendicular to the capsule segment. We don't know which face we're actually looking for, but if you think about it geometrically, we've detected overlap with some convex face, so we know that it must point towards the contacting body and thus points anti-parallel to the contact normal. The perpendicularity check isn't mentioned by Dirk, but I did find it helpful in removing some false positives. After we exit the do while loop, we check to see if a reference face was found. If one was found, we'll attempt to stack the capsule on top of it. First, clip the capsule segment against the side planes of the reference face. Once the segment has been clipped, project the clip points onto the reference face. These will become your contact points. To calculate interpenetration, take the clip points and calculate the distance from them to the reference plane and then subtract the capsule radius. If no reference face was found, however, just simply use the hull contact point as the collision point and return true. If GJK fails, like in the sphere case, we assume a deep contact and perform SAT. However, I have unfortunately been able to get a test configuration where I could build out the deep contact, so for the time being this will have to be a forlorn to-do statement for future need to solve. Finally finishing us out for today is hull versus hull. For this one, we skip straight to SAT and define overlap as simply being the absence of a separating axis. This is going to be a quick one because it's almost all black box for now, but the general idea is to run the SAT between the two hulls and catch the two faces and edge pair with the least interpenetration. If we do not detect any separating axes, we'll first test for an edge contact, but first this stuff I'm going to just copy in since it comes right from a post that Dirk made. So we first check for the edge contact by seeing if its distance is greater or basically less negative than some epsilon value computed between a relative and absolute tolerance, as well as the least negative face distance. Should the overlap between the edge be less than the overlap epsilon returned, we generate an edge contact, which is basically just a cross product between the two edges, and we use the reported overlap for interpenetration. If the edge contact is not the minimizing contact, we next check face 1 using the same epsilon calculations against face 0. If we generate a face contact using hull 1, this will be the reference hull and hull 0 will be the incident hull. The contact normal is set inside the convert face contact function, but comes from the reference contact face. Since the normal needs to point away or towards body 1, we invert the contact normal when moving it to world space. Finally, if we have no other options, we generate a face contact with hull 0 as the reference face, or as the reference hull, and hull 1 as the incident hull. The contact normal will no longer need to be inverted, only moved into world space. And finally, after conversion, we return true. So that's about it for today. Thank you all for your time. Thank you for watching. If there's anything you want better explained or would like more detail about, feel free to let me know. And I will see you in the next one with mesh collisions. Thank you very much.